Hi everyone, my name is Sirus Mati and I'm assistant professor in electrical engineering in the Department of Electrical Engineering in Kermanshah University of Technology. In this course, I'm going to teach you guys how to model and simulate different systems in Matlab. For the first session, I'm going to write the equations for an RL and RLC circuit here and then do the simulation in Matlab. Let's get started. Make it larger. Okay. Imagine I have an RL circuit like this, R, and in series with that we have an L. The input voltage is V and the output response is I. The only things I need to write is the equation, KVL equation for this circuit is V equal to R times I plus L derivative of I over T. And then the only thing I need is just write the equation in terms of di over dt like this. Di over dt is 1 over L V minus R times I. And using MATLAB blocks, we can solve this equation. Change the color to this. The blocks that I'm going to use is integration block, which is 1 over S, and then the gain block is like a triangle again, and then I use sum for doing summation like this, and then I need a input for this circuit, which can be a step or sine wave, and then another block I need is oscilloscope scope in MATLAB. The only thing I need to do is just integrate this term like this. 1 over S can do the integration. If I have di over dt here, it gives me I. And then I can multiply I by R and then do the summation over here. This is summation, V comes in, and then with a negative sign here and R here, using a gain block, I have Ri with a minus sign. This is the output here is this term V minus Ri, and then 1 over L gives me di over dt. This is a gain block, and this is the block diagram in MATLAB for this RL circuit. As you see, we have input here. This input goes here. I used sum, gain, and integration, and then you can use, for example, scope to see the response of this circuit. The next circuit, I'm going to write the equation for that is change the color to green. Number 2 circuit is RLC C. Circuit. Imagine I have R and then L. Parallel with that, I have C. Capacitor. V input, R, L, and C. I have IC, IL, and I over here, and then with another color, I have the voltage over here is plus minus V over C. KVL and KCL for this circuit gives me these equations. Change the color. I can write for this current I V minus VC, V minus VC over R. Okay, and then this current is the summation of IL and IC. This is IL plus IC. And then I can get IL from the equation for an inductor, which is equal to IL is 1 over L integral of voltage over the inductor is VC dt plus this term is C dVC over dt. Make it clear. This is IC, current in the capacitor, and then for IL, I use the equation for an inductor. Notice that this VC is the voltage of capacitor as well as inductor. So using MATLAB blocks, I can draw the block diagram for this circuit. I need to start from here. The term that has derivative in it, I can say that dVC over dt is 1 over C. This term, V minus VC, V minus VC, and then over R. I'm here, then minus 1 over L, 1 over L, the integral of VC dt, and close it here. Let's draw the necessary blocks in MATLAB. First, imagine I have dVC. Change the color to make it much more better and clear. Imagine I have here dVC over dt. If I use an integration block, 1 over S, I can get VC. And then if I have VC, I can do another integration in order to solve this term, using 1 over L as a gain, 1 over L, 1 over L, VC over L, and then integration 1 over S, 1 over S gives me the integration, and this is 1 over L. This is actually the IL. This is IL. And then I can create this term over here in the input part, V minus VC. I have V here. the input V minus VC. VC is here, so easy. V minus VC, like that. Divided by R, I use a gain block, 1 over R for this part. V minus VC over R, and then minus IL. So I have plus minus. This is IL that I have here. Goes back to the inputs part. And then now this is all the terms inside. It needs to get divided by 1 over C. Again, 1 over C. And this is dVC over dt. I only need to connect these together. So this is the block diagram necessary for this circuit to be implemented in Matlab Simulink. Let's go back to Matlab and do this simulation in Matlab. Let's do it. In Matlab, I open Simulink and create new model. Okay. This is a untitled file. The blocks I need are 1 over S or integration. I write here in English, integration, integrator. Integrator is used here. It doesn't work, so let's go to library browser and find integration over here, add to untitled model. Okay, it added over here. Commonly used blocks. I need the blocks I need are sum, add to block. I need a scope, add to block, and then I need some input sources for this circuit step, add to model, and then I think that's all I need. The input, the scope, the plus sum integration. Okay, I need 2 of them. And then I need gain. Gain doesn't work. Let's find gain over here. Where is the gain continuous? Commonly block gain over here, add to block. Okay, good. I need a gain over here. Connect them together. This is, and I need 2 of this. 1 over here. Let's have a look at this circuit. 1 over S, 1 over L. Go back to Matlab. 1 over S, 1 over L. 1 over L. Inductance. And then go back to here. 1 over S, 1 over C. 1 over S, 1 over C. Copy and paste here. This is 1 over C. And then, sorry about it, this one. sum from IL. Okay, let's change the direction. I have minus and then plus, and then the line goes here to make it appropriate. This goes to IL, and then this one, let's see, goes to gain 1 over R, another gain here. This is 1 over R. Okay, that's it. And then this is minus sign, which comes from VC. VC is here. VC comes from here. And then input comes to this part. And I'm going to see IL and another block for VC. Okay, this is VC. And that's it. But the problem is that our parameters are C and L are undefined. If I push the run button here, it gives us error that says C, R, and L. I don't see the L, maybe L is defined. Okay, let's check the errors and make them clear. As you see in my workspace, L is defined appropriately. So I clear all of them. I clear all. So you see no variable is in the workspace now. It's much better to open a file and write all the equations in new script. It's much better. I use CLC for clear screen and clear all to clear all of the variables in the workspace. And then I need R, which I write 1. And for L, I write 1 again. RLC 1. This is an easy example, and I'm going to run this and save it. RLC underline parameters. That's it. You see RLC are defined and have values in workspace. Go back to Matlab and run it to see what is the step response of this RLC circuit. For IL, let's see what I get here. As you see, the step is an input which comes at t equals to 1 second, and then the rise of current, and it goes to 1 ampere at the end, which seems like correct. Let's go back to circuit and see what's happening in the circuit. Here we have the inductor current equal to 1 when V is 1, and this is in the steady state time. So VC is constant, and IL is equal to 1 over 1 ohm here. So that is completely correct. 1 ampere here, and then I expect VC to go back to 0 when the IL here is constant. Let's check the VC over here, which goes back to 0. It is completely right. And then the important point is that since L and C are very large, 1 Henry and 1 farad for inductor and capacitor are very large values. So you see the output reaches to the final value in more than 10 seconds. I can change the values over here very easily. For example, I write 1K for resistor, copy 1 millihenry for inductor, and 1 -6 microfarad for capacitor, and then run the simulation again. Go back to simulation and run it. This time I expect the circuit to be very fast, and I see the result over here. The result, the step jumps in t equals to 1 second, and then I see the result. I don't need to simulate this circuit for a very long time. The only time I can see is here. I can use the zoom tool over here to see what's going on in this part. This is the response of this circuit for the given parameters. As you see, it oscillates. After some oscillation, it goes to again 10, or I can say 100 milliampere amps. This is the current, I think. Okay, good. And let's have a look at VC. VC is here, goes back to 0 after some oscillations. It goes to 0. As you can see here, the output response is not as we expect. We can change the solver for this simulation. It gets much better. Control E opens the configuration parameters for us. The solver can be changed to, for example, ODE 23TB. Most of the times it gives you much better answer. Let's do it onto 1.5 and see the result this time. As you see, the response is much better. Sinusoidal, it gets lower and lower exponentially. There is an exponential curve over here, and gives the final result, which goes back to 10 times 10 to the -4. That's completely correct. Actually, this is 1 milliamps, which is completely correct because of the resistor value, which is 1K, and the input voltage is 1 over 1K gives us 1 milliamperes, which is completely correct here. Okay, this is the simulation for this circuit. We can simulate the RLC circuit using the elements in power library of this Matlab Simulink. For example, imagine I have a resistor branch. If it works here, resistant branch or branch RLC series RLC branch. It doesn't work, but branch again, branch electrical specialized power system fundamental blocks elements. I can use this directory to find the series RLC branch electrical specialized must be here. Simulink, Simscape, electrical specialized special power system, fundamental blocks, and elements. All the elements are electrical source and elements. You see the elements over here, RLC, series RLC branch, add to block, and then electrical sources. I need a voltage source, constant voltage AC, DC, AC, controlled current, DC voltage source. This is the DC voltage source. And then I need, what else? I think that's all. RLC input and scope. It's enough. I put the input voltage and then make a copy like that. Turn this, for example, and this rotation. This is L and this is C. I change this to R. Okay, and the amount of this, the value is R. And here I have L, and change this to L, and this is L. That's all. And change this to C, just capacitor, and this parameter is C. I'm going to connect this together, and they are connected here. This is connected to this part, and this is connected to this part. That's all. What I have here is okay, the VDC, VDC. That's all. Need to define in M file over here, VDC, VDC equals to 1, and run it. And now I have R, L, and C. I need measurements over here. What's that? VDC, okay. This VDC, RLC. Just let's run it. There is a problem. This voltage failed to value the mask. There's a comment. Okay, the problem is power GUI. We need power GUI for this circuit to be simulated. Power GUI, electrical special power system fundamentals block. Okay, it doesn't work again. Go back to library browser, fundamental blocks, and power GUI is added to this block. That's all I need. Now it needs to work. It must work this time. Oh, it's working. Great. But I need to measure the voltage and current, voltage of capacitor and current of this inductor. In order to make these measurements, I need to go to measure, voltage measurement, voltage measurement. It is in specialized fundamental blocks measurements. Let's go back to library browser. Specialized power system measurements are here. I need current measurement and a voltage measurement. That's all. Connect this plus and minus sign to the capacitor, and then current of this, let's clear. The current goes to here and then goes back to inductor, and then the output of this goes to oscilloscope, and then another one for this current. Okay, now run the simulation and see the output voltage of this capacitor. It is completely 0, which is not correct. No, it's working, but 10 to the minus 17 cannot be correct. Okay, it's almost 0. There is some changes, but not correct. There's a problem here. I can work on it. Tools, the initial state 0. Okay, the problem is here. The initial state is 0.001 for series RLC branch I of inductor. It must go back to 0. Okay, to 0. Okay, now run the simulation again. We have to get same response from this circuit diagram and this block diagram. Over here again, let's check the results. Okay, this time the response is correct. The only difference with this one is that the input voltage VDC comes in time 0, but in this circuit it comes in just the second one. Let's change it over here. If I put this step time to 0, I get same responses. And I just need to, for example, simulate this circuit for just 0.1 seconds. Okay, this is VC, as you see, VC shape, and then VC shape over here. This is one scope and this is another one. I need both of them. Seems similar, but this goes to 0.03. There are still some differences between them. Yeah, there is still differences between them. Let's check. Okay, I was mistaken. This VC, this is VC, and this is VC. Yeah, that's now completely right. Okay, as you see, the VC in both circuits are same. And for IL, this is IL 20, then back to 10. And here for IL, we have, yeah, for IL 20 back to 10. Okay, they are completely correct. As you see, we have simulation blocks and then the real circuit, which gives us the same results. Thank you for watching. If there is any comments, let me know in the comments part, and subscribe for this channel if you like the videos, and have a great day.